to continue with the presentation of Manolo, showing some applications of the software that we usually call cg-FEM. Okay, so he explained the hard part of the software. I'm going to explain the soft part, which is the applications that we are interested in. And well, this work has been in collaboration with Professor Rodenas, that is just presenting after me, and Manolo, and well, these are our students, Justo Javier, José Manuel Navarro, and these are two doctors of the hospital in Valencia, La Fe. Well, which is the use that we are trying to do with this cg-FEM technology? Well, normally, from the medical images, we have a series of CT scans. Well, that is, let's say, grayscale images. Okay, and sometimes we have a CAD model that is perhaps an implant into the mandible. Okay? So, which is the standard procedure? From these CT scans, I have to run a process to generate a 3D model of the mandible. Okay, so this takes time because here I have not the explicit CAD geometry. I have an image. I have some slices. I have to build the 3D model. Then, once I have the 3D model, I can put the implant, that is also a 3D CAD model. And now I can use standard finite element code, and I can run every analysis. And why we are doing that in general? We think that this is because all standard finite element software needs a CAD to generate the mesh. But once the mesh is generated, the CAD is not mandatory to be there. So we just need the mesh. So if I have to generate this CAD model just to make the mesh, why do I need this step? The question is, can we go from here to here directly, avoiding to generate the 3D CAD model if that's not available? So this is the motivation of this presentation, and it's one of the use that we have for our code. Well, which is the idea? How does we do it? So imagine that I have a slice, the CT scan or whatever. So for me, this is a grayscale image, and these in red are the finite elements. So in this if I take these elements, I can observe that into this element we have several pixels with different colors. What I'm going to do when I integrate the stiffness matrix of this element, I will consider the material properties into each one of these. In this case, each one of these blue points can be an integration point. So I'm doing a sort of homogenization here, without considering explicitly the boundary of the problem. The boundary is weakly considered into this formulation. So then, when I have this grayscale, the material properties, there are some relations between the grayscale and the Young modulus and the Poisson ratio. Okay, we take that from literature. We are not making the experiments to have that. We just take these values. So if you give me these laws, we can't generate the stiffness matrix directly without considering the geometry explicitly. Okay? So if I want to perform this integral properly for linear elements, I will need, let's just say, 4 integration points into each one of these grayscale pixels. And in some time, because if I do that, I have a lot of integration points into the element, sometimes we use only one. And in the next slide, we will show other things that we are using here. Well, how this method works? We have the image and the initial mesh, and of course, if I take, for instance, this element or any element like this, I'm going to observe that there is a large grayscale gradient into the element. So if I perform here the homogenization, this kind of homogenization, it's not properly homogenization, it's just this kind of integration of the stiffness matrix. What will happen is I will commit a lot of error. So what I do is I divide this element until the grayscale gradient into an element, a finite element, is below a certain value. with that, I can pass from this image to this image without any finite element analysis, just considering the grayscale distribution into the pixels. Okay. So here I implicitly detect what are the boundaries of this bond, for instance. Well, this case, okay, it's this finger. Okay, it's not the other one. I have this finger. I just take this, for instance. Can I apply direct boundary conditions? I just only need to define this geometry where to apply the boundary conditions. For instance, in this 2D is just a line, and the Neumann boundary conditions another line here. This is the only thing that I have to define. Nothing to do with the geometry. So I run the model. I generate the finite element mesh, and then just I solve it. Okay? And I have, for instance, the one misses stresses into the element or whatever. So this whole moves. This is a 3D mandible, so this mesh is performed only in 55 seconds using MATLAB. I generate the full finite element model of 2 million nodes. Well, some words with the integration, I can use like what we call Riemann sum. That is, well, into each one of the pixels that are falling into the element, I put an integration point. Okay? Well, this is not exact because I will need 2 integration points per pixel. So this will provide the exact integral in this case. But this is expensive. So the next approach what we are using is to perform a least square fitting here. Okay? And just to use a standard integration rule. This is the 2D case. Well, this is more accurate, but I have a lot of integration points. For instance, if I have 8 by 8 elements by time, I have a lot of integration points in the element, and it's expensive and excessive. This is more simple, but I have not a lot of accuracy. And in this case, if we use this least square fitting, we have an accurate result. And the B matrices can be shared between elements, okay? Because if I evaluated B matrices into these integration points and are the same for all elements, I can parallelize this process, and this is a low computational cost. Okay? Because since we are taking the same element and the same integration points into the element, all the elements of the mesh have the same integration points because it has the same information. If I consider these 2 approaches, since each one of the elements has different number of pixels into the element, I cannot pre-compute all the B matrices. So, what about convergence of this? We are using this problem, which I have a exact solution. It's just a cylinder under internal pressure. And here in this image, what I do is a pixel model of this problem with 128 pixels in each one of the directions. So this is the pixelization of this. That is something similar that we will obtain from a CT scan. If I perform an analysis considering 4 Gauss points per pixel, okay, or per element, I will obtain these results. As you can appreciate, because of the lack of accuracy on the geometry, I will obtain stresses that are not the ones that I will usually obtain with a standard finite element CAD geometry. But the problem is that this is the information that I have. I have a CAD geometry, I have a pixelization of something, an image. So we are having here, there is an error, but this error is not because of the finite element analysis, it's because of the lack of accuracy of the geometry. So, if we run this test, if this is the energy norm that we should obtain, if I'm having a fixed number of pixels, so for coarser meshes, I have more pixels into each one of the elements. For instance, here I have 32 times 32 pixels into this element, 16 times 16 pixels into the element, 8 by 8, 4 by 4. So when I'm refining the mesh, of course, I'm getting closer to the exact value. But what's happening here? I'm not converging here. I'm converging at this line. What does it mean? That the geometry that I'm solving is not the analytical one, the one of the standard cylinder or but it's another one, and this error is due to the pixelization. So what's happening? It's not necessary to go to 1 pixel per element or 4 elements per pixel, because around 2 or let's say 8 or 4 pixels into one element is enough. I will not get a lot more precision, accuracy, with increasing the number of elements, because I have a geometrical error that is coming from the image. So it's not, there is no sense in going farther. Well, if I plot this in the convergence, what's happening is that when I'm crossing the line, just I'm tending to the error level due to this kind of the energy error due to the bad or the lack of accuracy into the image. So our method, in this case, we can see that we preserve the convergence rate for linear or also for quadratic elements. But when I reach the error level due to the image, it's stopped. Well, what happens if I refine the image? In this case, I can refine the images, whatever, or not. So if I start to refine the image, of course, I'm getting closer and closer and closer to the exact value, both for linear or for quadratic elements. But in this case, as you can appreciate, the behavior of quadratic elements is not that smooth than the behavior of linear elements. So the question that we ask is necessary to increase the order in this situation, or not? It's something that is open today. So in this case, what we are doing is just taking this finger, applying here, this is boundary conditions, pressure here, whatever. We run the mesh, and we also check if we start making a uniform refinement on the image, we have this convergence. Okay? But if we use this adaptive technique according to the gray scale, we obtain this convergence that is, and we have higher accuracy with less degrees of freedom as expected. This is normal. And what is important here is that this process with the uniform least square fitting, instead of placing one integration point into this each pixel, just taking this least square approach, we obtain similar results, and the computational cost is smaller. So what are the applications that we are using now? This is a densitometry. Okay, this is just a plot that the doctors give us. So from this plot, we are interested only in this area. So the densitometry, the information that usually doctors take from the densitometry is just the bone mineral density. That is the mean value into this area. So with that, the doctors say, okay, if this bone mineral density is in the green area, you will not have problem on your femur. But if you are in the yellow or in the red area, you have some risks to have a fracture. Okay? But what happens is 40% of the patients that were in the green area, they have a fracture. So we can do something here. We think that one of the possible reasons is that if they only take the mean value, the bone mineral density here. But when a fracture starts, it starts just from a point. If there is something local here, if you take a global parameter, it's not possible to detect it. So with this technology, what we do, we take this image, okay, we just define this, where is this part of the geometry, okay, which is interesting, this part of the femur. We apply some load here, we restrict some of the boundary conditions here. We can only, we analyze it, we generate the mesh, we clean use something that is outside, that is not necessary. Then we run the finite element code, we analyze it, we put and then we take, for instance, the von Mises stresses here. And this process can be performed in just 1 minute, because the user only has to define where is this line, and apply the load. And this load can be related with the weight of the patient, so that the bone mineral density is something that is not considering at all. So with this computational time can be included in the standard medical diagnosis process. It's not something, well, and what we are considering that they use with the bone mineral density are not considering. We have some information at each point. Well, I have to consider, I have to take into account that this is just a 2D image, it's not a 3D image, so, but it's information that we have. We can consider, as I said before, some local defects, for instance here. We also implicitly is the length, and also is the diameter implicit in the model, because we take the geometry. We can consider the weight of the patient. And we would like to add some other results, because are important, if the patient smokes or not, the sex of the patient, and all this information we are thinking in the future to add with some machine learning algorithm to learn some the history of some patients. Is this information valuable or not? It's important to know the stress field into the femoral head. Well, these two situations are fracture, okay? And in this one, the green one was in the green area. So the doctors say that this patient will not have a fracture, but then it had. So what's happened? The bone mineral density in this was 0.9, and in this was 0.5. Okay, but what's happening here? The weight here is 76 kilograms. The weight here is 40 kilograms. Okay, but what's happening here is that the diameter here is higher than this diameter here, and that then if we run the stress process, the stress here are similar. So the doctors just take care of this value, but this value has also given some information. So it's important also to have an analysis, a stress analysis to determine this. Well, another application is just to put implants. I start the presentation. So I have the mandible, I have the fine-tailed model. I can just apply a force here, or I can obtain the stress field of the mandible. And also, if I take a part of the mandible, I can put an implant here and apply some forces and get the stress in the mandible and also in the implant. So how this part works? Well, I take a part of the mandible that is surrounding the implant, I apply some boundary condition in these planes, I put a force here on the implant, and I just have to take out, to delete the pixels that are falling into the implant. Okay? In this way, I generate the surface contact into the pixel model. Okay? It's just taking, I have the cut geometry of the implant, I just delay the pixels falling into the implant, and with that I generate the negative of the implant, and now I can apply what Manuel explained before, all the contact theory that he just explained before. So, if I consider complete adhesion, that means I forget about the contact, I just put as into each one of the elements the material properties of the implant. So this is complete adhesion, it's part of the material, it's stick there. Or the frictional model, that is the model that Manuel explained just before, which are interacting with the geometry of the mandible. So the stress field, the bone stress field in the implant is different. So this is the case of total adhesion, this is the case of the friction. This is the results of the sigma ZZ when I apply these forces. This is another way of thinking for the YY stress field. And this is stress field in the mandible, this is the implant there. Well, as a conclusion, that the cg-FEM methodology can analyze in an easy way geometries coming from images without the need of generating a CAD model, both for the CT scans or for the mandible implants. We also observed that the least squares fitting for the material properties it's accurate and it's fast. And we would like in the future to consider other information for the diagnosis. For instance, information not mechanical, information for the sex, the steroids, the age, or whatever, and introducing this in a machine learning algorithm to use this tool for prediction of fracture risk or another illness that the patient has. Many thanks for your attention.